Right answer. Yeah, okay. Nice to see you. We're here today. It's E637, and I'm back again, for good or for bad. And we're going to pick this up with the next section, which is color imaging. Okay? So, let's see. Today we're going to start talking about color. I actually talked to you a lot about color already. It's like I gave you the famous example of the cube, the color cube, and the color constant cube. And convinced you that everything you know or believe you know is wrong. Okay? So therefore, now we can move on to the next step, which is to try to say, now that you've rejected everything you believe, now what are you going to? We have to rebuild your knowledge, okay, from that set. So if we can't tell you what a color is by making physical measurement. So if I make a physical measurement, at least at a point in space for sure, I can't tell you what color you're going to see from the physical measurement at that point, because the same physical measurement can produce two entirely different percepts of color under different situations, right? So is it hopeless? I mean, what's an engineer to do? Okay? Do you just give up? Okay? So the answer is, well, okay, you step back. Oh, by the way, whenever you get a question like you're in the job and your employer says, we've got to do this, okay? Do you okay? So one answer you can give the employer. So when it's something you have absolutely no idea how to do, right? Okay. One answer you can give is, well, we took a class and we learned that that's impossible, so we can't do it. That's answer A, okay? Answer B is I have absolutely no idea how to do this and I give up, okay? Answer C is, gee, I'm really excited about this and I'm going to figure out some really clever way, which I really don't know what it is, to get this thing solved. I'll get back to you later with some good ideas on how we can move forward. So which is the correct answer? C, okay? Engineers never give up, okay? You never declare failure, okay? You just redefine the problem to something you can solve, okay? So, yeah, that's good advice, especially if you're on a job interview. Okay, now, so the measure of perception. So what are we going to do? So we know we can't solve the problem we wanted to solve. So we have to redefine the problem to something new that we can solve. Okay. So the new problem we're going to redefine it as is what, and really the only thing we'll really be talking about in these in this course is we're going to talk about the problem of how to match two colors. So when the percept is the same so when we can create two stimuli which generate the same percept. We won't know what that percept is, but we'll just know that it's the same. Okay? So this is, let me see. Okay, actually I need to go ahead one slide. This is really what I was just talking about. So two colors are the same if they match at all spectral wavelengths. That's clear. I mean, if you believe in deterministic kind of interpretation of the physical world, okay, then you believe that if a single individual human is provided with the same stimulus input twice, they should have the same response, okay? So now if it's two different humans, you would hope that they would have a similar response also, okay? Now, so if you reproduce the physical stimulus precisely in all its attributes, of course, then you should have matching colors. But what we're going to find out is that, in fact, color displays, are typically red, green, and blue, right? So that's not infinite dimensional because the number of wavelengths between 400 and 700 nanometers, there's a lot of degrees of freedom there. So how is it that with only 3 colors you can match the infinite number of degrees of freedom of the wavelength of light between 400 and 700 nanometers? Well, the reason is it's going to turn out that you can actually accurately match a color with 3 degrees of freedom. Okay, and roughly speaking, those 3 degrees of freedom are called the tristimulus values. So that color percept is a 3-dimensional subspace is one way of thinking about it. Okay. there's a lot of issues because it turns out the three-dimensional subspace can be a function of the environment, okay? But at least for a fixed environment, it's a three-dimensional subspace. Okay, so the two colors that match, even though their wavelengths are not the same, are called metamers. So, just to illustrate this in concept, okay? If you have So I like to give an example of an experience I had once when I was going shopping with my mother-in-law, okay? So I was going to look for some clothing, okay? And I'm very insensitive. In fact, I'm like the worst person in the world to be a color researcher because I'm not really sensitive to these things myself. But, okay, so we went shopping, and I said, oh, okay, we had some pants and a shirt, you know, and we were, this was a gift, okay? And I said, oh, these look fine. And my mother-in-law said, oh, well, I'm not sure the colors match. So she took I mean, they were supposed to be the same color, right? But there were different materials. So she brought the materials over to the sunlight. And there she said, oh, you see, they don't look the same, okay? So under one lighting condition, the two colors look the same. Under another lighting condition, they didn't look the same, okay? So these two colors, even when they looked the same, they were called metamers because the stimulus that they were producing was really different. They just appeared to be the same, but under different lighting conditions, you could see that difference, okay? So we're gonna learn about this and understand why this happens. When we're finished with this, you're gonna mathematically understand why this can occur, okay? Okay, yeah.
So the experiment that you showed us in the first session for color, for instance, blue and the other, what was that?
Yeah, that was like this.
Are they? So
are they metamers?
Yeah.
No. Okay. So here, that's an excellent question. So those are two different effects, okay? So here they're not metamers, okay, because here, okay, I guess it's that yellow. And is that correct? Yeah, it's that yellow. And I think it's that. Which ones are the ones that match? I have to be careful because, oh, no, it's that yellow.
Yeah, this blue.
And it's that blue, okay?
Right.
So those two colors are not metamers. They're actually just the same color, like the same. It's not, well, okay, your percept is the same, but the wavelength of colors being reflected from the paper is approximately the same because the actual physical input to the printer in this case was the same. And the printer presumably is not a space-varying system, so it puts the same ink down there as it does here. So the actual light reflected off there is identical. So this is a different effect. Now, you could have the same effect if they were metamers, okay? Right? But these colors have the same distribution of wavelengths, okay? And yet, they appear to be a different color. Your percept is different. The other effect I'm describing is when you have two colors that appear the same, but the actual wavelengths of light are different. So if the materials are different, this typically happens. So for instance, now these days, with okay, so it used to be on cars, they have like a plastic bumper on the car, okay? And then, well, I don't know. Oh man, this is the worst car I've ever seen. Okay, but then this would be like the painted material. So you want the bumper and the paint to match. But you can try to match it approximately, but because the two different materials are different, they'll always be metamers in practice. Theoretically, they could match, but in practice, they'll always be metamers. So even if you match the color, if you put it in different sunlight, you'll notice that the colors are typically different. Okay? So two different materials that are metamers will match under one lighting condition, but not under another. Okay? Now, in an emissive case, if you had an emissive display, but basically the metameric effect occurs when two different things appear the same color, but really have a different distribution of wavelengths. So for instance, I'm just going to draw some silly thing, but you would have two different, say in both cases these are the spectra, okay? And I'm just going to make something up. I mean, this is not true, okay? But if you had something like this, okay, and then you had something like this. okay? And it might be that these two distributions of light look the same, okay? Because when you take the subspace that you can see, you can't see the difference. They're clearly different, but you can't see the difference. That's a metamer, okay? So this is a physical effect that that the two light distributions are physically different, but they appear to be the same, okay? This is a different kick. This is color constancy. This is color appearance. So this is about matching colors. This is about the same color given under two different presentations appears different. Okay? It's a good question. You ask a lot of good questions. Okay, good. Okay, now, my explanation of this is a little bit circular, so bear with me, okay? Hopefully it'll all come together in the end, and this is not the same as an in-depth treatment of color imagery. I mean, there's another course taught by Professor Allbach who goes into this in more depth, okay? So this is kind of an introduction, so we won't cover everything, but hopefully at the end it'll sort of pull together and make sense, okay? So let's say you have some reference color, I of lambda. So we're thinking of a kind of an emissive situation here where you put in a psychophysical experiment, so there's some stimulus provided to you visually. You're looking into, say, some experimentally designed contraption that's designed to present a certain distribution of light to you, okay? So, and the reference, so there's two dots, okay? You're going to have one, so you say that the background is either gray or it might be black. You look inside of a box, say, so that you don't have anything else in your field of view. There's total control. And maybe it's dark, okay? It was one case, or it could be a neutral background. And then this is one color, and the one color is I of lambda, okay? And then there's going to be another color, another patch, and both patches are large, and you can adjust this color so that this color appears the same as this, okay? I don't know what the color looks like. All I know is that they match, okay? And since the surround for both, by symmetry, okay, unless it's the case that, you know, your left-right vision is different than your right-left or something. So, you know, if you flipped it like this way, okay, you wouldn't expect that to change the color, okay? So, believe me, you know, so unless your left and your right brain are different and your left and your right eyes are different, these should appear, if this was I of lambda and this is I of lambda, then in that case they should be the same. They should appear the same color, okay? So but now we're going to vary, say, this one, so it's not I of lambda. It's something else, but we'll try to match the colors. What the color is, I don't know. All I know is that it matches, okay? This is about color matching, not color perception. Okay, so now, in order to control the color of the second patch, what we'll do is we'll actually have three sources of light. And we're going to informally name the three sources of light. We could name the sources of light Larry, Moe, and Curly, okay? But instead we're going to call them red, green, and blue, okay? The red, green, and blue could mean anything, but we're just using those designations. It may or may not actually correspond to what you perceive as red, green, and blue, okay? But in general, this red source of light is going to be distributed towards longer wavelengths. The green is the middle wavelengths, and the blue is going to be the shorter wavelengths, okay? So now what happens is that now what we're going to do is mix the three sources of light together with positive coefficients. They can't be negative. So basically what happens is this. You have three sources of light, and you control the amplitude of the three sources of light either by modulating, say, the power to the source. When you modulate the power to the source, you might actually control unintentionally. You might shift the distribution of the wavelengths. So there are other techniques. You could put a spatial light modulator in front of it, and spatial light modulator turns off and on, say. But you could turn it off and on really quickly and control the duty cycle. So that way you're sure you don't change the wavelengths of the color of the light. The distribution of the wavelengths is the same because it's either on or off. All that you change is that you have a neutral gray change in intensity, okay? And you mix these three together, okay, and then you get a new color. Now, what that means is that the way of thinking about it, and you may have been like to a science museum sometime in your life, you know, where you had a wall here, right? And you take 3 flashlights. All right. And the 3 flashlights are 3 different colors: red, green, and blue. And you control the intensity, and then what'll turn out is you put red, green, and blue on the wall at the same time, you'll get white. Okay. Now, anybody who is a designer will tell you that there's effectively an infinite number of whites. The white is a very generic term, and you can have a lot of different things that people will call white. Okay. So if you put a little more red in it, it might be actually what they would call a warmer white. If you put more blue in it, it would be a cooler white. So you could have little shifts in color. But roughly speaking, if you put red, green, and blue together, you're going to get something approximately white. Okay? So now, so what happens now is you have this. So what you do is you adjust the amplitude of the red, green, and blue light sources until you match the reference color. And then when you match the reference color, you write down the values of R, G, and B. These are the tristimulus values. They're going to always be positive because you can't have negative light, right? So you'll have 3 positive values. And so the idea here is you're matching a color rather than trying to achieve some perceived color, right? Now, what will happen is this. If the reference color is, let's say the reference color is a very saturated red. Okay, so there's these standard words, okay? One is called hue, well, lightness. You know, if a color is, if you take like a display, okay, and you modulate the intensity of light coming in the display, right? The lightness increases as you get it brighter. I mean, bright. You have something being brighter or darker, okay? So that's one axis. Then the other thing is you can change colors. So you can go from red to green to blue, like the colors of the spectrum, okay? The color, as you pass through the different colors of the spectrum, you're changing the hue, okay? Now, the third axis is the saturation. So you can think of the colors of the spectrum as like this, okay? So you start over here in, say, I don't know, red, okay? And you go around the colors of the spectrum, and over here you have blue, okay? And then you can come back, and over here is purple. Purple, okay? Over here is like orange, okay? So, and in the middle is white, okay? So as you move away from the center, you're increasing the saturation of the color. As you're moving around the circumference, you're changing the hue, okay? So this is hue. This is saturation. And now the third axis, which you can't see very well here, is you can make it brighter or darker. So that's kind of going into the paper, okay? And that's lightness, okay? These are informal concepts. So for instance, what's more saturated, pink or red? Red, right? So pink is just a desaturated red. If you add more white to pink, to red, you get something pink, okay? All right. So, okay, now, let's say this is a very saturated red. And that, let's say the primary red here is not very saturated. So now the problem is going to be, no matter what, you can't match this. What you can do is you can turn the red all the way up, and you'll turn the green all the way to 0, and you'll turn the blue all the way to 0. But no matter how you adjust this, you can't get these two colors to match. Because this thing is more saturated than this, right? So what you can do is you can say, well, what I kind of want to do is I want to take this blue knob here, and I want to turn it down. I want to turn it past 0. I want to make it negative. but it doesn't go any further. Okay, so you're like, oh gosh, what am I supposed to do? Okay? So what are you to do? So here's answer A is it's theoretically impossible, so I have to give up. Okay. B is I don't know what to do, so I'm not going to try. And C is yes, boss, I'm going to come up with some strategy because I want to keep my job. Okay. I want to remain employed. Okay. Okay. So come up with a creative strategy. Da, 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 da. Okay. Any ideas? What are you going to do? All you have to do is look at the next slide.
Turn down the reference color.
You can turn down the reference color. There's a thought. Okay? I see. That is an engineering response. Give this man a hand. Okay? He did a good job. Okay? Be resourceful. Break the rules. Okay? Okay. But now the problem is. Okay, I'm good with that. Let's break the rules. But the thing is that it still doesn't quite solve the problem because I'm still not going to match this color because even as I turn it down, it's still not as bright, but it's still as saturated. So what am I going to do?
Desaturate it.
Yeah, I have to desaturate it somehow. How am I going to desaturate it?
Add white.
Add white. Or you can add one of these colors. Because when I add one of these colors, which of the three colors would I have to add if this is red? To desaturate it.
Add G and B.
You have to add G and B. Because if you add green and blue to the red, it's going to bring it towards white, right? Mm-hmm. So now you can bring it in, you can pull it in into scope, in the gamut is their technical word. And now you can match it. Now what will happen is that you can think of this like an equation. You can think of this like an equation. And the equation here, when you add the red, green, and blue to the reference color, you desaturate it, right? And when you add the red, green, and blue here, you're trying to match it, right? This is like an equation. You want these two sides to be equal, right? So when you have an equation like that, you have R is the reference minus, I don't know, alpha times, I shouldn't use R for reference because that's like red. I'll call it C for color, okay? This is minus alpha times R, and then equals, I don't know, whatever. This might even say beta times G, okay? That's like the same thing as saying C equals alpha times R plus beta times G, right? So, I'm sorry, you're adding this here, right? So this becomes subtraction. So when you move it from one side of the equation to the other, what you added to the reference is like subtracting from this color. So this is like having a negative value of the primary. Now in practice you can't add a negative value of the primary, but you can in concept, and you can achieve the same result by adding it to the reference. So what you do is you adjust these knobs, okay? But it's to get the best match you can, and some of the knobs may go to 0. For the ones that go to 0, if it goes to 0, then you take the corresponding knob here and you start increasing it. You could come up with some kind of mechanism, like a mechanical. If there's a mechanical engineer in here, there could be like a thing where you turned a knob, and when you turned it past 0, it would start increasing this one, and then when you turned it down here, it would start increasing that one, right? So now you control. You don't want both knobs on at the same time, because if you do that, you'll just cancel out. I mean, technically it's still correct, but it'll make it harder to make the measurement. So the R then is R plus minus R minus, and the G is R G plus minus G minus, and the B is B plus minus B minus. So these values RGB now can be both positive and negative. They'll be negative if you had to add some RG or B to the reference color because it was too saturated. Now what we can do is, now there's a thing called Grassman's law. Grassman's law says that the color perception is a three-dimensional linear space, okay? So it says that if I have two colors, I1 and I2, okay? And I1 has, okay, this thing here, these values here, RG and B, are called the tristimulus values. And for each distribution of color, for each I of lambda, we get a different set of tristimulus values. So there's a one-to-one mapping between the I of lambda and the tristimulus value. So we have human subjects, we have them do the experiments, and we insert different I lambdas, and each time they make the adjustment and we record it. So for each I lambda, we get a set of RGB values, the corresponding tristimulus values. Now, the mapping from, so we have like two sets. Imagine that we have I1 of lambda maps to R1, G1, B1, right? And I2 of lambda maps to R2, G2, B2, right? So now the question, so we empirically measured this. This is not a mathematical result. This is just an empirical result. We put subject in front of it. We perform the experiment. The question is, will all people behave exactly the same? Well, no. All people won't behave exactly the same, but most people will behave similarly, right? There are some differences. By the way, we have to take a person with normal color vision. If you're colorblind, then there's going to be some other things happening, okay? So take a person with normal color vision, and they'll pretty much give you the same response, okay? Now what will happen is this. Grassman's law says that if I produce a linear combination of these, so if I take I1 of lambda plus I2 of lambda to form a new color, I3 of lambda, when I go to perform the experiment, getting the tristimulus values, the values of the tristimulus values will be R1 plus R2, G1 plus G2, and B1 plus B2. So by adding the two distributions of light, what the response I'll get will be a linear combination of the tristimulus values. So Grassman's law is an empirical law, but it's actually motivated by what's going on in the retina. In the retina, the cones in the retina are sensitive to the distribution of photons, right? These lambdas quantify the distribution of photon energy as a function of wavelength. And the cones in each of the three kinds of cones in the retina, the long, medium, and short, are going to have a sensitivity which is proportional to a weighted sum of the photons as a function of energy. I mean, there's good reason for that to believe that's true, because if you look at the biochemistry of basically the way the cones in the retina behave. So this part of this Grassman's law is really not dependent upon a high-level understanding of how humans process color or images in their central nervous system, in the brain. Okay. It's more a function of just how the retina behaves. So it's a pretty accurate model. As you're going from the continuum of models that describe the physical world that are very accurate until you get into the models of human vision, which are very kind of high-level models of human perception, this is sort of on the low-level side where the model's pretty accurate. But it can vary from person to person, like, for instance, if there's issues having to do with color blindness. But even in that case, it's going to be a linear subspace, okay? It's just that this mapping in tristimulus is going to be different. Okay, so if you believe this is a linear mapping, this is basically saying it's a linear system. So the most general linear system, so if I know that, if I take, what this is saying is that if I take this thing, I put it into a box, and I get an output, RGB, that this mapping, this is linear. Okay? The most general linear system I can write for this is, okay, if this was a discrete vector, then the most general transform would be a 3 by n matrix, where n was the number of discrete variables in here. Okay? So a matrix is the most general linear transformation. In this case, it's a little different because it's a continuous function. So the most general linear transformation is that I get R is the integral from, whatever, 400 to 700 nanometers of I of lambda d lambda times R of lambda. Okay? I'm calling this R0. And so this is the most general linear transform. So if you believe Grassman's law, then the relationship between the incoming light distribution and this tristimulus values has this form. So now all we have to do is calculate what the distributions of these weighting functions are for R0, G0, and B0. So when you have a linear time invariant system, and you want to know what its impulse is, well, you want to characterize the linear time invariant system, what do? I kind of gave you the answer. You put an impulse into it, right? And you see that's one way. Either that, or you could do like a bunch of frequencies. Okay. Now this is not a linear time invariant system. It's a linear system, but it's potentially time varying. But you can characterize its response by putting an impulse in at every wavelength. Now, an impulse as a function of wavelength means that you're going to have an input color of a light distribution, which is concentrated to a single wavelength, and that means it's a very narrow band source of light. One way of producing that is with a laser. Okay, and right, you can also use other sources of light, which are, these days, like LEDs will produce pretty narrowband sources of light that are not coherent. But laser is sort of a typical way of doing that. So what you do is, in order to solve this problem of characterizing, I forgot to mention something, which is that these functions here have a name. These functions, first of all, they're simply parametric unknowns in the equations. But they have a name, and they're known as the color matching functions. We'll see why later they're called that. But basically, they're the functions which you have to integrate the light distribution by in order to find the tristimulus values. And going back, remember, the way we found the tristimulus values was by doing the color matching function. Okay? Now, so how do you solve for the color matching functions? Because if you have the color matching functions, then you can calculate the tristimulus values for any light distribution. So what you do is this. You say, I'm going to put in a source of light which is spectrally pure. Okay? So it's going to be an impulse at a particular wavelength, lambda 0. Right? And, okay. So if I do that, and I integrate, what do I get? I get that the value of the color matching function evaluated at that one light wavelength, lambda 0. Okay. So if I do this for every value of lambda 0, then the tristimulus values that I get will be at every lambda 0 will be the value of the color matching function. So what this says is I can do this experiment by running this color matching experiment here. The reference color I give is a pure spectral wavelength going from 400 to 700 nanometers. And for each case, I adjust these parameters until I get a color match. I record the values of R, G, and B. And what I'm basically doing is reading off the color matching function as a function of wavelength. Now, there's a few questions that come up at this point. One is, well, what are the R, G, and B? I never said what R, G, and B was. Well, they can really be anything you want in theory, okay? As long it'll be just a matter that the tristimulus values you get will be in terms of those particular color primaries that you happen to choose. But in practice, you want these R, G, and B values to be as saturated as possible so that you get the broadest spectrum, broadest gamut of colors you can produce. But remember, even if you didn't pick them to be the broadest, very saturated, you could still match the functions by doing this trick here. Okay. So now, using this whole methodology, you can measure the tristimulus functions. Now, there's been a few. So the tristimulus, the color matching functions, are an empirical result because they're not the result. They're not. Pi. I'll write on here. Pi, right, is not an empirical quantity, right? I mean, it's not like. Well, in fact, I don't know if you know this. I'm not proud of it, but I've got to tell you because it's just too good a story, okay? Which is that apparently it's actually true. I read the article somewhere that the state of Indiana attempted to legislate the value of pi at one point. And thank goodness, before they passed the piece of legislation, I think it was a Purdue professor showed up and talked them out of them at the last minute so that they wouldn't be like, it would have been an embarrassment they would have never lived down, okay? Because, pi is the ratio of the diameter to the circumference of a circle, right? So that, I personally believe, is a concept that transcends human thought. It's kind of exists independently of the physical world, okay? Okay, now, but this thing we're measuring here, the color matching functions, this is a property of humans. The mathematical structure we developed for measuring it is one that's an abstract mathematical framework. But the actual measurement itself then just depends on humans. So you have to just go out there and measure it, right? It's like you could take a compass and try to make a really precise circle and measure it, but that's not how people calculate pi. They calculate on a computer using formulas because it exists. It's not a physical measurement, right? Okay, but here, this is a physical measurement. We need to make physical measurement, and we fit the data, okay? So there's been a number of attempts of that over the years, and CIE is the organization that's most broadly recognized for having done this, and they have different standards. They have the 2-degree observer and the 10-degree observer, which depends on what the size of the dot is when you do the color matching. And I think most people almost everybody uses the same model. Oh, there's actually a third model. When people use LMS, long, medium, short, the psychophysics people actually don't conform to the CIE standard. They use a different distribution. But they differ in small ways, okay, first of all. And in commercial applications, most everybody uses the CIE standard, and I think most everybody uses the 2-degree observer, okay? Is that correct?
They use the 10-degree in the automotive industry.
Oh, really? Oh, that's interesting. Okay, so I'll put this automotive. But most everybody else uses the 2-degree observer. Okay, yeah. So the 2-degree observer is almost universally used, okay? There's some exceptions, but almost universally used, okay? So, now, these are fine differences, okay? So, okay. Now, okay, fine. Okay, so this just reviews what we've already discussed. You have a tunable laser in concept. You change the wavelength from 400 to 700 nanometers, and as you change the wavelength, at each wavelength you match the light, okay, and you fix the total energy in this thing, and then you get you fix the energy in the color matching function, and then you get the 3 relative values of R, G, and B, okay. so you get the tristimulus values, which are would become as a function of wavelength, are the color matching functions. Okay. Now there is, and if you plot those, this is what will happen. You get these three curves, which go negative, because at this wavelength, you have the color is. First of all, I forgot to mention that I have to specify, for the purposes of making the experimental measurement, I have to specify what the primaries are going to be. So the primaries for this purpose, they make them pure wavelengths because it's an easier thing to agree on, basically. So it's going to be 700 nanometers, 546.1 nanometers, and 435.8 nanometers. Okay, so those are the three wavelengths that they use as their primaries. These would not be primaries that would be practical for real applications, because if you have primaries that are such narrow band, that means that if you had a display, for instance, the display would have to be, the red channel of the display would have to be purely 700 nanometers. That would be an expensive display to make, because real materials may be red, but they're not going to be that pure red that you would get with a laser. Okay, but for the purposes of making an experimental measurement in a laboratory, this is fine. It's not practical for fabricating real devices. Okay. So this is the experiment you do. Okay, and then these are the curves you get for the red, green, and blue components using those primary colors as a function of wavelength. Now, what happens is that at the wavelength of 700 nanometers, you know that the blue and the green have to be exactly zero, because the red is 700 nanometers, so you can match a 700 nanometer source with another 700 nanometer source. So if the red is a pure 700 nanometers, and you're matching a 700 nanometers, you don't need the green and the blue. So these are two of the colors are zero here, and the other one is greater than zero. Okay, and at 546.1 nanometers, two of these are zero. Okay, and the other one is non-zero. So at that crossover point, that has to fall at 546.1 nanometers. Okay, and at 435.8 nanometers there, those have to cross over. They're both zero, and the only one that's non-zero is the blue. Right. In between, this red has to go negative, because you have to actually subtract some red from the color. It's too saturated. Okay, now, so let's just kind of review this again. So the color here is a combination of the red, green, and blue times their associated tristimulus values. So the tristimulus values are scalars, and the red, green, and blue are vectors corresponding to, you can think of the primaries as vectors, which you're adding together in combination, weighted by the scalars, okay? So the red is, you take the color matching function associated with red times the incoming light field, you integrate that, and that's the tristimulus for red, green, and blue, okay? So now the value of this is that you can match the color I lambda by using these weights of the primaries, okay? Okay, now there's something that I kind of smoothed over, okay, which is how do I scale the red, the green, and the blue, okay? So there's kind of a factor here that I ignored, which is the intensity of the red and green and primary, okay? So you sort of want to scale the amplitude of the red and the green primary so that when you add equal, whatever that means, amounts of them, so equal would mean that red, green, and blue, or when this is 1, 1, 1, you want the combination of this to be white, okay? But how do you define white, okay? So that gets into this whole point of of white point. For now, what we're going to do is we're just going to assume that the color matching functions integrate to 1. So we're basically just scaling these to have unit area under them. Okay. So okay, now. You need some points of reference here. So white, as I said, can be many different colors. So the way we're going to get, but we need to have a point of reference. Okay. So we have over here 400 nanometers to 700 nanometers, right? And the amplitude here is 1. Okay. Okay. So this is an amplitude of 1. So if we have light, so we have the amplitude of 1, that means the amount of energy per unit wavelength is constant. So if we measure the energy between two wavelengths, so let's say we have a sharp cutoff, and we just take the energy, it's constant. Okay. Now, if we do that, if you show this stimulus to an observer, they're going to perceive some color. Okay, and so you could find what the tristimulus values are going to be for that. So this thing here is called equal energy white. This is equal energy white. Okay. So if we normalize the color matching functions to integrate to 1, then if we take the integral of these functions with this distribution, we're going to get that I of lambda equals 1 is going to transform to a color matching tristimulus values of RGB equals 1, 1, 1. Now, equal energy white is not necessarily what you would call a neutral. Well, I mean, you might call it a neutral white. I guess it's a matter of subjective opinion. It's probably a bluer white than you would normally choose as a white. Okay, but it's a standard reference. Okay. It's not actually used as the white in applications all that often, but it's a point of reference, okay? Okay, now, now what happens is this. Okay. One of the problems at this point is that the color matching functions are negative, which is sort of okay, but not entirely great. So the color matching functions can go negative. So if you have a camera and you wanted to make the camera so it would capture red, green, and blue, and if these are your primaries associated with red, green, and blue, now this means that you have to have a camera which has negative sensitivity to photons at certain wavelengths. Now that could be done physically, but it wouldn't be very convenient. What it would mean is you'd have to have, let's say, instead of 3 colors in your camera, you'd have to have 6. You'd have to have one color for the positive part of this red, and one color for the negative part of the red, and then electronically you'd have to subtract one from the other after you captured the photons. But that would be not a fantastic way to design a system. It would add to cost a lot, okay? And it wouldn't. So see, the question is, can I capture the same 3 tristimulus values with color matching functions which are strictly positive? And the answer is you can. You have to use what's called the XYZ color coordinate systems. And we're running out of time. But basically, you find a transformation which has the property that the color matching functions of the resulting transform coordinates are strictly positive. Once you have that, then the color matching functions kind of look like this instead of going negative. Now, you'd say, well, this is great, but it turns out that there's no free lunch. Because what will happen is if you have strictly positive color matching functions, then the primaries associated with them are no longer real physical primaries. They're what are called imaginary primaries. So we'll talk about that next time. It's a very interesting idea. Thank you very much. Bye.